Right, hey everybody, welcome back to another edition here. I'm working in your textbook today. I'm on page M1-131. And this gives a pretty good overview of what we're doing, modeling a problem situation. So it's more of adding some context, adding a situation to solving quadratic equations or functions. So instead of just being given like, f of x equals x squared plus 5x plus 6, we'll have to come up with the function rule all by ourselves. So hey, in this one, we've got a sheet of metal that we're going to try to model into a drain, and we're relating the height of the drain to the bottom width of the drain. So hey, I'll kind of try to visualize this for you using this little Post-it note. So hey, what we could do is pretend that this is our sheet of metal, and we're trying to create a drain out of it. So as it stands, this length down here, or the width, I should say, the width of our metal sheet is 8.5. Now we don't have any heights though, I mean, it's just paper thin. And so to create the drain, what we're doing is folding up each side to get a height. So maybe I'll try to do that for you. Going like this, and I'll fold my other side, show you what it looks like here. So again, we started off with 8.5 on the bottom, and then after folding this and cutting some of the pieces off, we've now got a drain, and our drain has a height to it. Okay, so hey, when the height of the drain is 0, the bottom width is 8.5. Again, whenever it was 8.5 on the bottom, after folding up my two sides, then I'm going to get some height. So when I started with 8.5, I've got no height right there. All right, so 8.5 for the width, 0 for the height. Now we'll pick a different height. So looks like we go from 0 to something to 1.5. So let's make the height of our drain in feet. I suppose we can do 0.5. So if the height was 0.5, what is the new width? There's a lot of thinking here, a lot of thinking involved. This is, a height of 0. If I fold up this flap right here, and this height is 0.5, I do the same thing on this side, and its height is 0.5. What's the width now? Hopefully I'm explaining this clearly. So it used to be 8.5, the width of this bottom section, but I folded up this flap, and this flap has a height of 0.5. So if I do that on both sides, I fold this up and I fold that up, I'm taking away 1/2 right here. I'm taking another half right here. So hey, the bottom width in this case is actually going to be 7.5. I've taken off a half here, a half there. So like 1/2, I get down to 8. I take another half, then I'm going to get down this bottom width is going to be 7.5. All right, so let's keep on building up this table, and then we'll eventually come up with the function rule. So the next height, let's make 1. So instead of cutting off a half from each side of our sheet, we're cutting off 1 foot. So I'm going a little further here. I got 1 foot, I'll fold that flap up, I'll cut a foot off here, and then I'll fold it up. And that's how we're making our drain. So if I take 1 away here and 1 away here, the width is going to be 6.5. Okay, if I take off 1.5, so I'm taking 1.5 on this side, then I'm subtracting 1.5 on this side. So essentially on the width from the 8.5 that we started with, I'm taking away 3 feet altogether, leaving me with 5.5. All right, let's keep going with that same kind of pattern. So we'll go with 2 here, 2.0. If I take 2 away to make the height of the drain 2, I'll take 2 here, 2 there. That leaves me with 4.5. Okay, fantastic. We'll start taking away 2.5 feet from each side of our metal sheet, leaving us with a width on the bottom of well, that's like 5. So 8.5 minus 5 will give us 3.5. Okay. If I wanted to make the height of the drain 3 feet, if I took off 3 feet on this side and 3 feet on that side, folded them upward, what's left on the bottom? That would be 2.5. Okay. Now, what should we go with here? Let's go to 4. We wanted to make the height of our drain 4 feet. So again, on this one, we started off with 8.5 feet altogether. But what if I cut 4 feet off right here and then cut 4 feet off on the other side and then folded those up to make our drain? So our drain is going to be looking like kind of like this. Pretend that these things just got cut off and folded upward. Again, so this little piece here is 4, this little piece here is 4. So when I fold them up, that's why my height is now 4. My height of my drain is going to be 4 feet. What does that leave down here though? Since I've taken away 4 and then another 4 for 8 altogether, the bottom width is going to be 0.5. All right, not a lot left there. All right, and then this one is kind of just hypothetical. This situation is not actually going to make sense. You can see that if I increase the height of the drain by 1 foot, the bottom width was going down by 2 feet. For every 1 increase in height, like when I went from 2 to 3, my width went from 4.5 to 2.5. It went down by 2. So hey, if I increase the height by 1, the bottom width is going to go down by 2. So this is going to leave my bottom width as negative 1.5, which doesn't actually make sense in this situation. This one is like nonsense. This is not going to happen with our real world scenario that we're working with. So hey, question number 2, the engineer needs to identify the measurements that allow the most water to flow through the drain. What does the engineer need to calculate and what does she need to consider? Well, a drain that's really thin like this, it's going to have a lot of pressure. There's going to be a lot of water trying to squeeze through this really small width. So we need to pay attention to a couple things, of course. We need to pay attention to the length. We need to pay attention to the width. And also we need to pay attention to the overall area. We want to maximize the area of this drain. What does she need to calculate? Well, hey, let's calculate a function. Let's calculate a function and relate that to the area. Okay, let's go to the next page. Hey, so they give us a nice little diagram here of what's going on. To determine the drain dimensions that allow the most water to flow through, the engineer must calculate the cross-sectional area. The cross-sectional area of a drain is shown. So they've got a width of the sheet and they've got some height already folded up. So this is what we're trying to maximize. We want the largest cross-sectional area. So we don't want something that's like super, super thin like this. This cross-sectional area we don't want, or even something really tall and narrow. That's another situation that's like not going to maximize the area. This uses the same length and width, but like these areas are a lot smaller than this one. So anyhow, determine how to determine the cross-sectional area of any drain. Well, hey, that's going to be pretty easy. Just going back to like elementary school, to find the area, you can just do area is equal to length times width. That's it. That's how you find area. You take the length by the width, multiply them together. Predict and describe the drain with the maximum cross-sectional area. So for predicting the drain that has the maximum cross-sectional area, I guess it's just how efficient is your drain? How efficient is that shape? So the shape that absolutely maximizes area is a circle. So in terms of polygons, you know, we want some stuff with like straight lines. Predict and describe the drain. It's probably going to look, maybe I can actually make this a sentence. The drain will look like a square. The drain will look like a square. So what that means is the length is going to be approximately equal to the width. I would assume those things are going to be pretty close to each other. Okay, so define the function for the cross-sectional area of the drain with a height of h feet. So we are coming up with the area or the cross-sectional area of the drain. So we do know that area in terms of height, okay, is going to be equal to something. What is the area as a function of height? So we need to go back to this drawing that we were making earlier. Whenever we had started off with 8.5 for the bottom width, and then we multiply that by whatever the height is. Maybe I can go back to the actual table that we got. So here, to find the area, if we wanted a new column here for area, you would go 0.5 times 7.5 equals area. So the height and the width here, right? We're just multiplying one dimension by the other. So when the height's 1, the width is going to be 6.5, and our area is going to be 6.5 square feet. This one, you would just do 1.5 times 5.5, and you get the area, or the cross-sectional area of your drain. So how we'll actually write this function is just think about the width first. We know that the width is 8.5, so maybe I'll just write that out. We know this is 8.5. We know the width is 8.5, but the width is changing. We're constantly taking something away from the width. We're cutting off a piece here. We're cutting off a piece here, and then we cut off a piece on the other side. Now, this length can change. The amount that we're cutting off on each side can change. So instead of putting an amount there, let's just put a variable. And the variable that we're going to use is h, because we know that this piece that we're cutting off becomes the height of our drain. So we've got an h here and an h here. So here our width is no longer just always 8.5. It's 8.5 minus however much distance we're cutting off here. So how you can write that out algebraically is 2h. 8.5 minus 2h. So that's our width. Now we just need to multiply that by our length, or in this case, height. And that's going to actually be pretty easy to do because just this piece that we cut off, this h, does become the height. So let's put an h there. Okay, use technology to graph the function. Let me grab a calculator real quick, and I can plot the function there and make it really clear for you what it will look like. Okay. So to graph the function that we just created, I'll do it in a calculator. So to graph on a calculator, graph a calculator like this, just hit y equals. Let me clear what's already in there. And so my function is 8.5 minus x. You will have to use x in this calculator. It won't recognize h as a variable. And then times, oh, I forgot to put 2x there, 2x times the height, which again, I'm just using x for my variable. Now I'll go to graph. Maybe if it's not showing up, you can go to zoom and then go to option 6. It should put a decent window in there for you. Okay, so there's our situation. That's what our parabola looks like. So use technology to graph the function, then sketch the graph. So this is what our function looks like. When the height's 0, the area is 0. That makes sense because, I mean, we don't have any height. We're not covering any. Any flat area. Maybe I'll make this kind of clear here. Let's graph our function. I'm just going to go ahead and start way down here, because the negative values are not going to make any sense for us. We're not going to have negative areas or negative widths or negative heights. So I'm just going to start my graph off at the origin at 0. That's all I really need to worry about. So my graph, it pretty well just looks like this. You can make a more accurate one if you want. But that's the gist of it. Again, this parabola, this is the area. So as the height of the drain increases, the area increases up to a certain point. So hey, my y-axis in this scenario is area, the x-axis is height. As the height increases, the area goes up, height increases, area goes up, but eventually our area starts to go down. So we want to know what's kind of that sweet spot. What is the vertex essentially of this function? What puts us at the peak of this parabola? What height gets us here? What height maximizes this cross-sectional area? Maybe we could go A of H here. Okay, cool. So let's move on to number 7. Analyze and interpret your graph. What is the maximum cross-sectional area for the drain pipe? Maybe I can do it on this. If I trace my parabola, it might just be a little bit easier to see. So you can see Height is 0. That was my x variable. Area is my y variable. It's also 0. As I start to increase, right, as my height starts to increase, my area starts to increase. Like when my height is 0.3 feet, the area is 2.4 feet squared. So the maximum area is going to be at the very peak of this thing. Looks like it's going to occur somewhere right around here, in between probably 1.9 and 2.1. I think if I go to second calculate and maybe I'll try to get the maximum value. The maximum point when x is 2.12, y is equal to 9.03125. So what's the maximum cross-sectional area? Just by looking at the graph. Maybe I'll say by analyzing the graph. Analyzing the graph. The maximum area is approximately 9 square feet. 9 feet squared. Identify and label the intercepts of A of H on your graph. So the intercepts, you have one right here, right? It crosses the x-axis right here, and it also crosses right here. So maybe I can try to get there. So this intercept is at, what is that at? About 4.3, something around there. I had my y equals 0. So 4.25 is going to be the answer here. 4.25 is the intercept here. Describe the meaning of each. So I suppose we can do this question first. Identify and label the intercepts of A of H on your graph. So H equals 0 is one intercept, and H equals 4.25 is another. Those are your two intercepts. Those are the heights. These are the heights. To interpret their meaning, kind of, these are the heights. These are the heights that give area equal to 0. By plugging in these two heights to our function, we will have areas equal to 0. Identify and label the equation of the axis of symmetry. So that should be pretty easy. The axis of symmetry, just going back to your graph that you create, is going to be cutting this in half, cutting the parabola exactly in half. And an easy way to find the axis of symmetry when you have the intercepts is just add them together. Add together the 0. I don't know why I wrote H equals. Just add together the intercepts and then divide by 2. Add the intercepts together and divide by 2. Very easy way to find the axis of symmetry if you already have the intercepts. Okay, so all you would really be doing is 4.25 divided by 2. So 2.125. That is the location of the axis of symmetry, 2.125. Draw and label the drain with the greatest cross-sectional area. Hey, so this was important. This axis of symmetry was important. That's the height that's going to maximize your area. So let's draw it then. We know that the height is going to be 2.125. We do have this width still. The other height is going to be as well, 2.125. And then this width would be, you know that we started off with 8.5 minus 2.125 minus, all right, so we started off with 8.5 altogether. I'm subtracting this, and then I'll subtract this piece as well. So 2.125 again, and I get 4.25 for the width, not the height. The width is now 4.25. Okay, in this problem, you built a new function. The area as a function of height is equal to height times 8.5 minus 2 times h, using two existing functions. Yes, we did. We had two functions put together. Identify the first factor in this function and its function family, then describe what it represents in terms of this problem situation. So it's just asking us, this first factor, the h, what is that really representing in our function rule? Identify the first factor. So the first factor is h, its function family. Well, hey, since it has an exponent of 1, you know, we just have the one variable there. It is linear. And in terms of what it represents for this problem, that just represented the height. The second factor, the second thing, this thing in parentheses, 8.5 minus 2h, 8.5 minus 2h. Hey, this also just has one variable, and that variable is raised to the first degree. And we don't even write the exponent there because it's just understood that if you have a variable, it is raised to the first degree. This is h to the power of 1, but you just never really have to write that. So it's also linear then. Anything to the first degree is linear. And it's not representing height, actually. This 8.5, and then we subtract 2 times the height. This was representing, in our situation up here, it was representing the width of our drain. Identify the type of function created by the product of these two factors. So for part C, if I go back to my graph, you should be able to tell what type of function is created. It's concave down, we had a vertex and axis of symmetry. So this is a parabola, and parabolas are quadratic functions. They're created from quadratic functions. So identify the type created by the product of these two factors. It is a quadratic function. It's not linear, it is quadratic. And you can see this if you multiplied the function. So it gave us a nice broken down rule up here, h times 8.5, and I subtract 2h. So if I distributed this variable, I can go here, I can go here, and I can rewrite this as 8.5h minus 2h squared. And it should be very clear now. For why does this happen? Well, we have an exponent, and the largest exponent over here is 2, h squared. Exponents of 2 mean you have a quadratic function. Okay, so I believe that's it. I'll go to the next page and just make sure that we're not going to be missing anything, and we're not. So hey, that's the end of the video, everybody. Thanks for watching. See you in class. Bye-bye.